Hello, everyone, and welcome to today's webcast from the Trusted Computing Group. I'm Mark Schiller, Executive Director of the Trusted Computing Group, and today we'll be talking about protecting intellectual property in the Internet of Things with trusted computing. We'll start with a few notes and reminders regarding logistics. Please double check to make sure you've got your PC audio on. Also, we're planning to have time for questions at the end of the presentation segments. Please use the Ask a Question function to type your questions as the event proceeds, and we'll do our best to cover as many of those as possible at the end. I'd like to start by introducing our presenters, Steve Hanna and Gunther Fischer. Steve is a Senior Principal at Infineon Technologies and also serves as Trusted Computing Group's Internet of Things Group Co-Chair. Steve leads Infineon's Internet of Things security team and also chairs several committees in the Trusted Computing Group. Steve also serves as the Security Area Directorate team on the Security Area Directorate team in the Internet Engineering Task Force. Gunther Fischer is a Senior Consultant for Licensing and Protection at WIBU-SYSTEMS. Gunther focuses on cybersecurity applied to the Internet of Things and advises software publishers on planning and implementing protected software systems. Our agenda today will start with Internet of Things security, including a survey of risks and countermeasures. Next, we'll cover IoT applications of trusted computing. And we'll close with a segment on protecting intellectual property, including software protection methods and secure licensing. To walk us through our first topic of IoT security, I'd like to welcome Steve Hanna.
Thanks, Mark, and welcome to everyone who's on the call today. We're going to talk about IoT security today, but the first thing we need to do is to have a little talk about definitions. When we talk about Internet of Things here today, what we mean is a world where physical objects are seamlessly integrated into the information network, where you're able to integrate a variety of different physical objects with cloud intelligence or local control. It's a broad definition, and it covers a lot of different markets and applications. For example, smart home, automotive, industrial, and ICT. But why do people care about IoT? Why do they want it? Well, it has the potential to transform all of these different industries. For example, in your home, you can have new capabilities and services. You can have the ability to remotely manage a second home, or for your home to wake up in the morning and automatically prepare the coffee for you. And in automotive, you have the ability to have self-driving cars. You have the ability to have remote maintenance performed without having to take the car into the shop, for example, for software and firmware updates. There's the ability to have greater efficiency, where your car, your electric car, can charge itself at night during the times when electric power is cheapest. And this is improving your cost effectiveness in charging your car and the overall system efficiency and even environmental friendliness. In an industrial application, IoT provides the ability to build to order, to build goods that are in high demand, and even to make a specific product directly based on a consumer's order. So all of these new capabilities that IoT provides are quite compelling from a financial standpoint, from an environmental standpoint, from an efficiency standpoint, from a business standpoint. And as we look at IoT, we see that it affects not just these well-known markets and industries called out on this slide, but also many others. In fact, you could say that almost every market will eventually be affected by Internet of Things. everything from the home to the industry, from the industry to the city to the country, and including our vehicles as well. So we can see that IoT has broad impact. That's great. Lots of potential. How does it work? Well, a typical IoT architecture has some devices which gather data and do some sensing. They send this data up through the network to some sort of a processor. Now, it could be a local processing, perhaps within a factory. It could be remote processing, such as cloud processing for a home. And in any case, this processor, this server, gathers the data, it may archive the data, it analyzes the data, and then it sends back some commands down through the network to the device where some action can be taken. For example, if your home gets too hot, that data might be sent up, and then in response a command sent down to increase the air conditioning. Or you could have a sensor in your car that indicates, oh, you're heading home, and in response to that, the cloud could decide to adjust your air conditioning. We shouldn't forget the handheld devices and others that are used by people to interact with the Internet of Things, because those are important too, especially as we get into looking at security issues. Now, speaking of security, I'm afraid that the number and the variety of attacks against IoT systems have been growing tremendously. So if we look back at the 10 years ago, they were largely theoretical attacks and papers that were being published. Then people started poking around with their own home systems, their own webcams, and realizing, hey, this is something that could be hacked. In fact, I can figure out what the default password is, and then I can hack somebody else's home security camera and use it to spy on them. There have been concerns and proof of concept attacks on medical devices. And in fact, there have been some very dangerous activities such as explosion in a pipeline in Washington State, which was very serious, demonstrating the way that these cyber attacks can have physical impact in the real world. In industrial environments, there was an attack on a German steel mill in 2014 that was able to cause massive damage to the equipment. And this was a cyber attack on IoT systems within the factory. Of course, you may have heard recently about the attacks on the Jeep Cherokees. This was not a physical attack, but a remote attack that was mounted through the cellular network, and they were able to disable the transmission and to basically remotely control this car while it was driving at highway speed with the reporter in it. Oh boy, glad I wasn't in there. And then just a few months ago, the attack on the Ukrainian power grid, which took place. They were able to cut power to 250,000 people, these attackers, for up to 6 hours. And this just demonstrates that the scale of these attacks, the impact of these attacks continues to grow, that it's not theoretical, that it's real, and it's happening on a regular basis. So, as we build our IoT systems, we have to build them with the understanding of these attacks and what damage they can do, and a good understanding of how those attacks take place and what are the countermeasures we can use. So how do those attacks take place? Well, each layer in this IoT architecture can be attacked, whether it's attacks on the devices, trying to introduce a false device into the system and therefore false measurements, or compromising an IoT device. The device level is certainly subject to attack, but people underestimate the level to which other layers in the IoT architecture can be attacked. It can be an eavesdropper just listening in on your network and getting some data. It can be an active attack on the network where data and commands are injected into the network. Or it can be an attack on the server, a remote server and cloud or local server. If you're able to hack that server and take control of it, you will be able to do some real damage because the server can send down commands to the system, to the devices, and remotely control them. So how can we defend against these IoT attacks? Well, there are a variety of different defenses, and there is no one silver bullet which will completely take care of the problem. But through a combination of defenses and what we call defense in depth, you can go far in defending against IoT attacks. So to walk through a few of these, we look on the left-hand side, authentication, the ability to authenticate the device, the network, and the server. Those are all essential. You can't have your device just accepting commands from anything, nor should your server be accepting sensor data from anyone without authentication. The communications should be secure because often confidential data is being sent, and that data could cause damage if it falls into the wrong hands, so you need to be able to encrypt it or otherwise secure it. Several others of these, boot process protection and secure software and firmware update, go to the ability to protect the integrity of the device and of the network and server as well. And I won't have time to go through all of these defenses, but I would encourage you to take a look at some of our Trusted Computing Group links that we have at the end of this presentation, which will give you more information on the topic. Speaking of trusted computing, and after all, we are the Trusted Computing Group, industry standards group, creating standards for trusted computing. Let me explain a little bit about trusted computing, what it is and how it can help with TPM, or with IoT rather. So the TPM, the Trusted Platform Module, you may have heard of it before. It's a standardized hardware root of trust, internationally standardized now that ISO has recognized the TPM standards created by Trusted Computing Group. So they're also known as ISO IEC 11889, or 89 as we like to call it in casual conversation. And what TPM provides is a set of benefits. It provides a foundation, hardware root of trust, hardware capabilities upon which secure software can be built. These are designed to be resistant to software attacks and even to physical attacks. You can think of the TPM as being sort of a virtual smart card for your IoT system. It provides strong identity for that system, so the ability to authenticate the device or the server. It also gives you the ability to do encryption with that device, because you can only really encrypt if you know what the destination is, who the recipient is. So together, this encryption and authentication capabilities, this constitutes strong identity for the device. And just to be clear, the keys are kept in that chip at all time, the private keys, never leave the chip. In addition to the identity capability, TPM supports attestation commands, and those allow you to do remote integrity checks on the device, whether it's the IoT sensors, actuators, the network, or the server. These two capabilities, which are really just two of the many capabilities included in the TPM standard, are fundamental, as we saw earlier in looking at basic IoT countermeasures. So why is it important to have hardware here? Why can't we just do those things in software? Well, if you remember the Heartbleed attack from a few years ago, you'll remember that there was a lot of pain caused when people stored their cryptographic keys somewhere that software could get to them, and then bugs and vulnerabilities in the software were used by attackers in order to get copies of their private keys. This graph basically shows the results of more than 40 years of research by a fellow named Capers-Jones. He has been researching software quality for many, many years. And what he has discovered, he's looked at hundreds of different projects at all different types of industries. He's discovered that there are benefits to having stronger software quality and process. And you can see here, if you really mess it up, you're going to have a large number of defects per function point, maybe 8 or 10 defects per function point per 1,000 lines of code roughly. If you do sort of an average job, you can get it down to 5 defects. If you do best in class, avionics grade, NASA, quality software development, you can get the number of bugs down to maybe 2 bugs per 1,000 lines of code. But you never get it down to 0. That's why NASA had 4 different computers, aviation computers, up in the space shuttle, because they knew they couldn't get the number of bugs down to 0. And what that means from a security perspective is that there are always some lingering bugs. Those bugs are vulnerabilities. Some of those are remotely exploitable. And long story short, you're always going to have some 0-day vulnerabilities in your software. So the best practice from a security perspective is not to store long-term secrets somewhere where software vulnerabilities could make them susceptible to attack. And that's why the hardware approach is superior from a security standpoint. And that's why so many different industries are using TPM for embedded systems for Internet of Things, whether it's automotive, financial services, industrial control systems, or whatnot. TPM is widely used in this area. All right. And now I'm going to hand it off, and we'll move on to the next topic, software protection and secure licensing with TPM.
Thanks, Steve. And thanks for the great introduction of why a TPM module is necessary. My name is Günther Fischer, and I also would like to welcome you to this talk about TPM modules and how to use a TPM module and leverage to the module to protect software, intellectual property, which is part of your software, and also use this technology that is already existing since a while to enable new license models for your software that is running either in an embedded device or in an IoT device. So this is basically the reason we saw at WIBU that we currently have a huge and great implementation for already existing systems like embedded systems, where we have our own technology right now that we leverage to protect software. And since a lot of computer manufacturers and board manufacturers already include TPM modules on their board nowadays, we saw that there is a strong demand from the customer side to also support TPM module as a secure element to store private keys into the secure element and make the device unique for licensing. And by recognizing that, WIBU decided to join the Trusted Computing Group by the beginning of this year and implement a technology that shows how to leverage the TPM module together with the since 27 years existing technology that WIBU provides to their customers, originally from the PC point of view, where high-end software that was usually very expensive was the main target currently. But since 5 years, WIBU decided to enter the embedded system market and provide the same technology to the embedded devices to protect software from an embedded device against tampering, sabotage, and also IP stealing from the device. So by doing this, we have a tool set that basically works like the following diagram shows. So you usually use your existing application, which is the binary that you get from your compiler and linker, and then you use a set of tools to protect this binary. And what we added is we support the TPM module as a secure anchor right now to store the private keys and make it as difficult as possible for a hacker to steal or compromise the private key. The tool that we use to protect the binary is called AxProtector, which is protecting the overall binary completely. And then we have a separate tool that is included in the AxProtector that allows to protect smaller methods or functions within the binary with separate keys, which allows you afterwards to license the binary and the functions in a demand version. So you have a feature of on-demand functionality that is enabled by this technology. At the end, we basically store a couple of keys in a trusted secure element, which is in this case now a TPM module, and it's something that we added to the existing product portfolio. So at the end, the customer will receive the encrypted binary, including the keys, which are shipped to him separately, which then rely on a secure storage, which is the root of trust, which is basically the TPM module. And if the combination is correct, the application will run and work for the end customer. So to be able to enable this scenario, we have a complete set of protection suites, which are available on all different kinds of platforms. And this is an overall view of this, which allows you to enable the CIA principles, which is basically confidentiality, integrity, and authenticity, which is what the TPM module enables as a secure store and a secure element to store the private keys within the TPM module without ever leaving the TPM module. So the technology behind this basically works like this. So you take your original binary that comes out of a compilation phase and the linker, which is basically unprotected. And then you use this tool that I already mentioned before, which is called AxProtector, which will act as a wrapper technology that will build a wrapper around your existing application, which will encrypt the code section, the data section, and also the resource section in your binary. And it will add an engine, which is called AxEngine, which will allow you to decrypt the binaries, the code sections, the data sections, and also the resource section at runtime. This is done automatically by using this envelope technology that's provided by AxProtector. And to store the real secrets, like the private key for the AES encryption, therefore, the technology leverages the TPM module together with another technology that we call CodeMeter Act, which is a file-based technology. In addition to the function that you can encrypt the overall binary, there's also a possibility to encrypt different code sections within the code section in a different way, which is done by a technology that we call IxProtector. IX basically means it's the individual protection of different code segments. This allows you to afterwards license those code parts in a different way, which allows you to implement things like feature on demand and also counting the amount of units that or the amount of usage or how often a person actually used the code section, and then basically decrement a counter that allows you to build pay-per-use models with this technology. And then you also have the possibility to combine the two technologies, so to have the AxProtector to protect the overall binary and also includes in this binary different sections that are protected in different ways. This allows you to protect your IP against sabotage, which will basically be recognized if somebody would modify the binary, the decryption would not work anymore. You would get a piece of garbage, so the execution couldn't happen of the binary. And also preventing somebody debugging your binary, because there is also debug prevention. And at this time, if somebody starts a debugger, the debugger will be detected and the application will stop working. So this is all done by this technology. And for this, we actually use the TPM module in addition to what we already had since the beginning of the year to allow this functionality to be used on different pieces of hardware and also on different pieces of operating systems as the underlying platform technology. So this is just a way how to look at it. So this is an example running on Windows. It's a simple example of an application that is protected by this technology, and the dialogues you will see are the standard dialogues, which are fully customizable and brandable to all the different brands that basically are going to use it. And then we, on the right, which is basically on the left-hand side, so if you start an application that is protected by this technology and you don't have the right combination of keys, the application will tell you that you have no license to run the application. But the full binary is already installed on the device. On the right-hand side, you see the technology that we use to visualize if a license is available or not, which will basically show you something that we call a container in a generic way, if there is a container available on the device or not. In this case, the application was started and there was no license on the machine that allows you to run the application. On the next screen, you see how to enable a license on a device. So basically, you can ship the device with the application on a device protected by this technology and providing no license for it. So, and if the customer decides to license the technology that you provided, he is asking for the license, which is basically the bullet point 1. He places an order which will be entered in your ERP or CRM system, which then will create an order in our backend system that will create a license for this end device. And this license will go down to the machine. The machine will read the license file into the machine itself, will create a fingerprint, which is currently based with the technology that we provide also on the TPM module. And the TPM module will make the device unique. This fingerprint will be sent back together with a ticket to the licensing system that we provide, which is our entitlement system. And this technology then will send a ticket back to the e-commerce system, which will then, to the CRM system, which will then be used as a bill of material element in the CRM system. And then the ticket, which is basically a 5x5 number or key, will be provided to the end customer. And the end customer can enable the license by just going to a web portal or using the technology underneath, and your application will do this fully automatically and enable the license. So this is how this would look like in a full-blown picture. So typically people send out a device with a base license, and then after a while the customer decides to enable additional functionality, which is the feature on demand part of the technology that I mentioned before, by requesting additional licenses for different parts of your application afterwards. So after you have distributed or deployed the license to the end device, this would look like this. So this application that I started before, which didn't have a license, will start, and then you can see within the application which parts of the application are licensed. So on the left-hand side, you see what's happening after you distributed the license. On the right-hand side, you will see that there is a license on the device right now. After the person is using the application for a while, he might demand additional functionality and is asking for an additional license for this part of the application, which is already on his device, but it is currently not enabled. So after going through the same process that you just saw before, he will receive an additional license which will unlock the functionality by the key that is stored in a combination of something that we call CodeMeter Act and the TPM module, and then he can just leverage and use the additional function that he licensed on a demand way afterwards. So the overall architecture of the backend system that I mentioned before looks like this. So we have a web server that is basically hosted in a virtual machine. This virtual machine contains everything that is necessary to do the license management. So you can connect this backend server to already existing ERP systems within your organization or corporation, or CRM systems, or maybe homegrown systems. You could also change the way how the database is used. So you could also use in-house databases that you already have to store the information that usually is stored in a MySQL database in the virtual machine. To get access from the outside world, we basically provide technologies like something that we call connectors that allow to connect e-commerce systems. So you could basically set up a web shop and people could purchase a license through a web shop. So this could be something like, let's say, Facebook for Internet of Things devices that go through this connector and order additional licenses for all the different devices within an organization. This could be done fully automatically because all of these functions are exposed as so-called subcalls and web services. So the web services underneath can be used by your application. By just calling the different web services, you enable the different functions in the license entitlement system. In addition, if you want to make it more comfortable and it's not a headless device, you have the possibility to add something that allows to do this from within the application without going to a website, but just implementing the same technology within your application and loading the license fully automatically from a gateway, which is then going through the virtual machine, which is then issuing the license, and then the license will be transferred automatically to the backend system. All of the things that I mentioned can be done either online, so the device is really connected to the internet, or offline, and in the offline case, this would be done through license files, and the transfer would happen as a file transfer. So you could use any transport mechanism, like emails, for example, or maybe FTP downloads to bring the license down to the device. And in addition, as I said, there is also a couple of pre-configured templates that allow you to do this on a web portal. So we have a license portal and something that we call a web depot, which can also be fully branded and customized. And then the end user would just use the 5x5 license ticket ID to pick up the license from a web portal. And then he could also, again, do this online, basically coming from the device that is connected, or through offline transfer via a file transfer. So, as I mentioned before, we had this technology for a long time, which is basically 27 years already. And we had a secure license file, which is a simulation of a secure element based on an encrypted file. We also have a solution that is already existing since almost half a year now for microcontrollers, which is a combination out of a secure license file and a secure flash part within a microcontroller. And we had an already existing smart card solution which is called CodeMeter dongle, and the secure license file is called CodeMeter Act. And now we added an additional combination between a secure license file and the TPM module to make the storage more secure by using the secure anchor that is provided by the TPM module. And this is basically the reason why we actually joined the TCG group by the beginning of this year. So, and I would like to thank you for listening and would like to transfer to Mark to go to the next slide.
Great. Thanks very much, both Steve and Gunther. That was very interesting information there. A couple of quick points for those of you in attendance. You'll notice on your screen there is a entry point to attachments and links that provide reference information around the topics you heard about today. All of those links that you'll see there should now be working and live, and those will allow you to get more information on the topics you've heard about, kind of dive down into our Architect's Guide, our guidance for securing IoT, using TCG technologies, and we've got other resources there as well. So I encourage you to take a look at those. Also, it does look like we've had some questions come in during the presentation, so I'll get to those in a second here. If you do have any questions, take a look on your screen. You'll see an entry point where it says ask a question, and feel free to just type something in there that may have come to mind as you've listened to the presentations here. I think I'll start with Steve for this one, and then Gunther, if you have something to add after Steve addresses it initially, please jump in as well. Steve, we've got a question that says, given its history in the personal computing space, how is a trusted platform module, a TPM, suited for the Internet of Things applications that might not have the same kinds of power, space, and other capabilities that we find in personal computers and servers where those resources are generally not limited?
And it's a great question. So TPM has recently been adapted to these more resource-constrained environments. One of the things we did with TPM 2.0 was to include support for more embedded system-friendly cryptographic algorithms, such as elliptic curve, and also new interfaces such as I2C, in addition to the more traditional LPC and SPI or PC-oriented interfaces. As for operating systems and demands upon the main processor, TPM is now being used with quite a variety of different operating systems. It's not just a Windows thing. There's drivers included in most of the Linux distributions, and now some of the embedded systems, operating system vendors like Wind River, including support for it. So we see adoption taking off across the IoT environment, definitely more and more popular in that area.
And I would like to add that in addition to the technology that we provided for the PC space, we created a special edition which is based on regular C source, which is fully portable. And if somebody wants to bring this library to its platform, which might be even a proprietary OS, that's possible. So you will get the source code to do the porting, and we will support you to do that. So, and just to give you an idea, so the size of this library can range from 120K to 300K, depending on the functionality that you're including into the library, which is fully specific to what you demand. So either you need local area network support, or if you just need the functionality that I mentioned before, a combination of something that's called CodeMeter Act, which is a secure license file together with a TPM module. That's all possible, and that's all just built for those smaller footprint devices to enable this, as I mentioned before. One of the application, which is a very small size of memory that you have, is the microcontroller example I had on one of the other slides, which is a Cortex-M device, which has only 1 megabyte of flash memory. So it can be used in this environment. So Mark?
Okay, great. Another question has come in. Gunther, I think this time we'll start with you, and then Steve, feel free to chime in as well this time. How is a trusted platform module supported in software for the Internet of Things? Are there development environments available? What are the support vehicles, drivers? What's available out there to support a TPM and IoT?
So it depends on the platform that you're going to use. So the example that I presented was running on a Windows environment. In a Windows environment, we actually currently use the crypto providers that are shipping together with Windows, which is basically the standard interface. And in addition to the Windows environment, it would be also possible to support browsers as the interface on non-Windows devices, and even on Windows if you only want to have one API that you're going to leverage. So these are the APIs, and the technology that we put on top is just the standard technology by leveraging the TPM module. So it's not a different version, it's the exact same version that we already provide since many, many years.
I'll just jump in and say that a lot of people in an IoT environment will just code directly to the TPM, and avoid the need to use an interface library such as the TSS. No harder than interfacing with any other peripheral. You just send some, pack your commands in binary format and send them out to the TPM.
Yeah, that's something you would do with the library, for example, if you have no concurrent situation talking to the TPM module.
Exactly.
Okay, great. Thanks, guys. So another question. Since a TPM is generally not visible to the end users, the user level for IoT devices and applications, how does a trusted platform module used in the IoT get set up and managed? I think maybe we'll start with Steve, and Gunther, ask you to chime in as well.
Sure. That's true. Most IoT devices don't have a lot of user interface, or if they do, it's dedicated to the function that they're performing, such as setting the temperature on a thermostat. Some have none at all. So generally, it's the manufacturer who's responsible for configuring the TPM and installing any identity on it, for managing it throughout its life cycle. But that's not inconsistent, and in fact quite consistent with the way that most IoT devices are handled. You can't expect that somebody's going to be tinkering with the user interface and setting security configurations on a device that doesn't have any screen or buttons on it, like a light bulb. So generally handled by the manufacturer. Sometimes they'll expose some of it through an app, but a lot of the times it just happens behind the scenes, and new software versions get pushed down to the device automatically, and certificate renewal and anything like that is handled automatically and remotely by the manufacturer. That's all the more reason why having some hardware in there is very handy, because if you're dealing with a software-only environment, you can't really have confidence in what the device is telling you. It could be telling you it's running one version of the firmware. It might just be a total lie, because once it gets infected with malware, it's just going to lie about its configuration. When you've got the TPM there, you've got that hardware root of trust to give you confidence that you know exactly what's running on that device, because the TPM has the measurements, and it's the TPM that's telling you exactly what's running on the device.
Okay.
So, and our technology is just reusing this hardware root of trust, which is preceded by the manufacturer, and adds additional certificates, private keys, private and public key pairs by just leveraging this secure element, which is never releasing the key itself. It's highly protecting it. And the rest is basically built on top of this. So it's all assuming that the key, the private key, which is the most important part of it, will never leave the TPM module itself, and it can never be compromised.
Okay, thanks. We've also had a question come in about the different packaging that's available for TPMs, just kind of a general question about the state of the marketplace. Is there still kind of a mix of both discrete implemented TPMs out there as well as TPMs that are integrated onto larger multifunction modules? Are we seeing that mix of those out there? And this time I'll start with Steve on this one.
Yep, still a mix like that. Generally, your discrete TPM gives you a higher level of assurance and tamper resistance, whereas your integrated TPM gives you a lower overall cost, lower chip count, which can lead to a lower cost and lower PCB area being used.
Okay.
There are even people who are doing what they call firmware TPMs, where the TPM runs in a trusted execution environment like Trust Zone. That again is a trade-off, a cost security trade-off. You've got a lower level of security, generally no tamper resistance, and some susceptibility to compromise of the TEE or of other trustlets. But it's better than no TPM or no isolation of your processes at all.
So, like Steve said, so as I mentioned that we are using the crypto providers that are shipped with Windows. It will also be possible to use the PTT technology that is provided by Intel by using the same crypto providers and just having the different implementation of the TPM device driver that is talking to the firmware implementation that is shipped together with a few of the Intel processors. But as Steve mentioned, this is less secure than having a dedicated TPM module, which is just there for doing exactly what it is intended to be used, and not just pure software implementation in the firmware.
Great. Thanks, guys. Well, I'd like to, at this point, thank everybody for joining us today, for your great questions, and we look forward to hosting you at a future Trusted Computing Group webcast or event. This webcast will be available for replay if you'd like to point any of your colleagues to it on the TCG Bright Talk channel within a few days. And thanks again from the Trusted Computing Group, and stay secure out there. Take care, everybody.